here's an example of the p dx plus q dy plus r dz. Here we'll do it in a plane. This will just be a p dx plus q dy example. Suppose I want to evaluate a function of x and y dx plus a function of x and y dy. Remember, that's just the vector line integral expressed in a different form. We have to do the same thing. We just have to interpret dx as dx dt dt, and dy as dy dt dt, letting t go from its min to its max along the parametric path. Here's number 33 out of your text. Suppose I want to evaluate integral y dx minus x dy. And suppose we want to do it around this triangle. What is the value of this line integral around the triangle? Like this is a force with components y and minus x. It's f equals yi minus xj. What's the work done around this path when I travel around this triangle? Well, I first have to write that this path is the union of three individually parameterized paths, C1 and C2 and C3, right? C is the union of these three. And along the first path, we can let x equal t and y equal 0 to go from 0, 0 to 1, 1 this way. By the way, I wrote this little circle here. This is a common notation. If you have a line integral around a closed path, you'll sometimes write a circle here, or sometimes you'll even put a little arrowhead on here to indicate which way you're traveling, counterclockwise or clockwise around a closed path. Alright, so here along the first segment, if I'm going this direction, x is equal to t and y equals 0 takes me from 0, 0 to 1, 0. That's pretty easy, but how about this one? This is the line that has y-intercept 1 and slope, well, let's see, rise of minus 1 and run 1 is slope minus 1. So it's got the equation y equals mx plus b with slope minus 1 and y-intercept 1 is y equals minus x plus 1, or 1 minus x. We can write that parametrically. We want to go this way up the path, so we can let y go from equal t, go from 0 to 1. And in that case, x being, rewrite this x equals 1 minus y, gets x equals 1 minus t. So on this path, we'll let y equal t and let x equal 1 minus t. We'll traverse this line. T going from 0 to 1 goes from this point to this point then. On path C3, we want to go down here where x is 0, but y, if we want to go this direction, is 1 minus t, t going from 0 to 1. And so these three paths can be written parametrically like that, and we'll write that the line integral c is equal to the integral along c1 plus the integral along c2 plus the integral along c3, each one y dx minus x dy. The line integral, the sum of the line integrals along the unit of these paths is then equal to the integral along c. Well, this one, right, we write y along c1. Y is equal to 0 and x is equal to t. We interpret dx as dx dt dt, but x is t, so this is 1 dt. And then x dy, well, x is t. Oops, maybe I should write it that way. Let's write it as t. And then y is 0, so dy is dy dt dt is 0 dt, so it's t times 0 dt, hence I wrote 0. And this integral is just integral of 0 dt minus 0 dt is 0, right? Now along the second path, C2, we want to integrate y dx. Well, y is t, and x is 1 minus t, so dx is derivative of this dt is minus 1 dt. And then minus x dy. X is equal to 1 minus t, and dy is derivative of y 1 dt. So I integrate 1 minus t dt minus. And then the last path, once again, x is equal to 0, so if I integrate, and y is equal to 1 minus t, so integrate y, 1 minus t times dx is 0 dt, right, derivative of x dt. Minus x dy, x is 0 multiplying minus dt for dy. This integral is 0 because it's integral 0 minus 0. Well, and then also the minus t dt here cancels the plus t dt here, and we're left with integral minus 1 dt, which is minus 1. So this line integral around the triangle, we did 1 unit of work around this closed path. Try the homework, and we'll move on to conservative vector fields. That's a very important case. Gravity, for instance, is conservative. What happens if this force field we're integrating here happens to be gravity or something?